Welcome to lecture 3 of Stats 1. Put Stats 1, there we go, nice big bold letters. We're going to take what we did in lecture 1 and a bit of what we did in lecture 2, combine them into something that's computationally a lot more feasible, and actually build a first real statistical model based upon probability. This is called the binomial model, and it's why it's called ups and downs. We can refer to what we did last time very easily, which was in lecture 1. We built this. We built this grid. We built this table with, well, red and green. We could have used green and blue, purple and black and white, purple and orange go very well together. Okay, anything that's binary, anything binary has an up and a down, an up and a down. It can either be on, which we will often code as 1, or off, which we will code as 0. And it can be repeated. If we're at 1, it can go up and down again to another 1 or a 0. This repetition allows us to map this tree structure that we're going to build to actual data and observations given an hypothesis, so that we'll actually be able to compute this thing over here. Plausibility numbers that we came up with: 0, 15%, 40%, 45%, and 0 again. It's a logical process, so we know it works all the time. It's a logical deductive process. It will necessarily happen if we set it up this way every single time. And in that sense, it goes beyond the notion of a heuristic and focuses on a set of calculations that are basically the same calculations all the time. What we're going to do this in this lecture is replace part of this set of calculations. We're going to replace some of these calculations that we did here in the ways. We're going to replace those with a formula based upon this idea. And this comes from several places, but probably most notably Jabob Bernoulli. And you can look up Jabob Bernoulli in a fairly well annotated Wikipedia article, which is right here. And it's got most of his major discoveries and works. It's got his picture over there. He's known for any number of things, but probably the most important thing for us is this thing called a Bernoulli process. You see a dice over there. He was very prominent he was a gambler. All right, let's go with that. But he used gambling models to help represent how to look at structures in data, things that were interesting to him. Like if I don't see the ship off the horizon, will it appear? Well, let's see how many times we've seen the ship on the horizon and it actually comes into port. One of the reasons for the development of the telescope wasn't just scientific interest. It was climbing to the top of a tower and being able to see beyond the horizon, beyond just taking a look with your naked eye. This is where we get the phrase, knowing is not just taking a look. It's a little bit more than that. And you can read about the Bernoulli process and its interpretation here. And you can get very mathematical about it, but we're going to try to keep our life as simple and still as useful as possible. We'll also refer to chapter 4 of the book that accompanies these lectures, which goes into a little bit more detail. Here's the heuristic structure we've been using all along, where we form hypotheses based upon a question. We parameterize it, in this case, with proportions. What proportion of the data is on or off, red or green, raining, shining, whatever our binomial setup is. And we work out that 1 and 0 set of combinations, throw data against it. We collect the rain, we collect an observation of clear days. We collect an observation of land, we collect an observation of water, whatever the dichotomy is. These are dichotomous variables, variables that are cut in two, only two possible values. And we figure out how many ways, given an hypothesis, could we have possibly found this data. And the hypothesis that wins, if there's a winning and a losing in any of this, is the one that's most plausible, and that's in the green at the end. The probability of a hypothesis given the data. And we're going to next look at a tree. You can see the sub little Bernoulli processes, also called geometric process. And then we're going to look at some paths through that process and ask the question, if I have 3 data points, how can it go through that information structure called a binomial tree, which is what this is. That's basically what we're going to do in this lecture, with a little bit of arithmetic, yes, represented by algebraic symbols later on, and learning again another aspect of counting with combinations. We'll take all of that to find the probability of seeing a particular observation given a particular, see that P right there, 0.25, hypothesis, and be able to calculate the plausibility of that. That's still not quite the plausibility. We have to look at the relative probabilities. We'll get to that and reconcile what we did on the work with land and water in lecture 1. Lecture 1 was good buildup for us, but now we want to burrow in and see if we can get a good algorithmic way that'll work with all types of binary data and won't crash our computers as well. That's going to be pretty important to us, because some of those numbers of ways can get into the 10 to the 120th power, which is real big. And then what we're going to do in part 2 of this lecture is build this model. We'll dispense with the bag of marbles, the bag of beans in this book, and just expand our horizons. We'll expand the number of hypotheses. You can make this up to 1,001 hypotheses, like 101 Dalmatians, Disney style. Just expand this like an accordion, and it's just a bunch of calculations. It is all the logic we are going to need, and we will be able to get this final plausibility result. Well, don't you think we'd want to, we'll do some spreadsheet engineering here. We would want to make a nice picture, and that's where we'll go with part 2. But before we make the pretty pictures, let's go back to our original 5 hypothesis story about land and water. Okay. So again, as I always ask you to do, or will always ask you to do, strap yourselves in, and let's get to this business at hand. Just making this a little bit smaller for us. We're going to continue to follow the 5-step analytical process. So this looks like a supply chain. And for those of you who don't like chevrons, I omitted this part of the chevron. Okay, I will continue to omit it. Some people don't like chevrons. I've worked for people, supervisors included. They say, what are you using a chevron for? It's horrible. Whatever. I like the arrow. Okay. And I like documenting like this. So we took something that was vertical before and we transposed it on its side. So we posed a question, and the question, remember, was literally how much water. We tossed a make-believe world around as a beach ball that actually it's almost ellipsoid, and wherever our right thumb touched water, we recorded that as a 1. And wherever our right thumb touched land, we recorded that as land, or a 0. So we formed several hypotheses, 5 in a grid. We're expanding our horizons. Horizon analysis is extremely important in analysis. We don't just look at one hypothesis, we look at 2 hypotheses. And we did that in lecture 2, just 2 hypotheses. We're not going to look at one, we're going to look at a competing hypothesis. We're going to say, what if it's not something? We used to call this contrary to fact. It's also a counterfactual, the idea of a counterfactual. And that is very, very important challenge that we need to put into these models and see where they break, see where they're different. Then we sampled, right? What did we sample? We sampled land and water. And here is, pick a nice blue for the water. Water, which we represented as a yeah, I picked out a green one. There we go. Pick one of these out. So we're actually using even more abstract, it's pretty physical, but it's a representation again of what is going on. And green. So we did this kind of a sample. Up here, out of the way. And we found this sample. We just did 3. We started with 1, looked at another and updated it, and we actually did some updating. And we showed what happened to that plausibility graph. Went from a straight line to a quadratic line to something that was quadratic but pinched in the middle. Okay, so we saw all of that, and just go back and look at that, look at your notes for that. And then we counted the ways. We took the sample and the hypotheses and counted the ways. So for hypothesis 2, okay, there was 1 way for water and 2 ways for land. Okay, we were able to calculate the number of ways we would see water, then land, then water again. And we took all of those ways, added them up, and look at them relative to one another to come up with plausibility. So in English, that's all we did. And if we look at the graph of what we did, last time. Should be right here. And let me bring up the Excel spreadsheet. Just take a second to bring that up. And after a mild break there, here it comes. Okay, we had four possibilities in the bag. We didn't know whether they were red, whether they were green or blue. Remember that. And that's how we coded them. There were 0 ways of getting water in the first, 1 way to get water in the second hypothesis, 2 ways in the third, and just the opposite. See, one increasing to 4, the other decreasing from 4 to 0. And we parameterize this with percentage of 0 out of 4 items in the bag as 0, 1 out of 4, 25%, and so on. And we even had a prior idea. I said this is an improper probability because it doesn't add up to 1. It adds up to 5. And we can make a 0.2, for example, to force it to be even all the way through. It would not affect our results in column K at all. And we collected 2 water in 1 land. And if we look at the formula for the water and the land, we see we took how many times water will be found under this hypothesis, raised to the named range called water up here in H2. So 0 to the second power, 4 to the first power. You got to multiply these together because of the counting rule we said, and it's a for each rule. Okay, go back and look at what that meant, but it's very much like the binomial tree rule that we'll be using. And we have 0 ways. And the next one is 1 raised to the second power times 3 raised to the 1 power. That gives us 3. And we get the number of ways and we add them up. And this is crucial. When we miss this point, we miss what we're trying to do. We're trying to do relative. It's entirely possible that these priors could be not all the same. They could be very low for some and very high for others, so that these ways, which take into account the prior, will change radically. And we need to add them up and we need to compare them reasonably with one another. And that gives us the plausibility index, otherwise known as probability. So we did all of that. And now we're going to do this again, but we're going to do it from the point of view of building a information structure called the binomial tree. And this is what we did last time in lecture 1. And we go back here. And stop fussing around. Find it. There we go. Sometimes it gets a little lost, like me. Okay, we're going to take one of these hypotheses. We're going to take, oh, I think I've got something worked out for P equals 25. Let me just use red. It's going to be a little bit better. So the way we can structure this is we can build a grid and deposit. And deposit a tree and grow the tree inside this grid. Now, what's the grid going to have? The grid's going to have basically ups and downs. This is called a branching process officially. It's got a name. Let's use it. Okay. And it turns out we have observations across the top, or they could be called trials, or they could be called whatever. But we're going to have repetitions of this process going over time. And this is a model that's used in so many forecasting applications, or it's the model that's underneath everything from option pricing in finance to sales forecasting in supply chain and marketing, forecasting fraud in a financial statement in an organization, to any kind of decision. This is often part of a decision tree. There's a lot of things we can do with this, and we will. Let me move this down a little bit. There we go, give it a little bit of space. And so for the first observation, we can either go up or we could go down. Now, if we go up with a proportion of 0.25. So what happens in the tree, that's 0.25 up. If you go down, it's 1 minus 0.25. It's the other thing. Okay, and we can interpret this almost as a probability of an up movement. Now we could also go start here and go left or right. Go left, go right. We could do that as well. And in in-person classes, that's what we do. Put some paper on the floor. We pick it up afterwards, of course, and mark out spaces. And that's the random walk. Okay. A lot of things going on there, and finance uses that a lot. But if you go up 25% of the time, you must be going down the rest of the time. 1 minus 0.25. So that's the first one. And the second one is, now remember what an up and a down is. But this is just the basic structure. Up, down, we're going to say an up movement is water. So this is going to be water. This is going to be water. And the down movement is not water, otherwise known as land, green. Green. So these are all the possibilities that can happen, and then we parameterize these possibilities with 0.25. Now, they're not our observations, but we are going to do 3 observations, and that's why we have to repeat this process 3 times. So let's continue that. Notice how they're meeting back up here. I'm not going to give you a mathematical proof that they would do that in this particular case, but the usual reason for it is that each of these observations are going to be independent of one another. That's part of the story. So we get this kind of very nice pattern. And this is actually typically called a graph. These dots are called nodes or vertices, a vertex. And these red lines are called edges. And if we put an arrow in it, it's called a directed graph. Okay, but that's math, but some important jargon for those of you who might get into the business of data analytics and science. Okay, remember all the downs are going to be green and all the ups when they finish are going to be blue. So this is going to be what? Blue or green? Right. This one's going to be blue or green. Ah, it could be either blue if it's going up, or green going down. Could be one or the other, depending upon the path it takes. Interesting, huh? Okay. But if we take this path, it's going to be blue, blue, and green, because we're defining a down movement as green. Any down movement. We start here and go down, it's going to end up green. But if we start here where we had green and go up, it's going to end up blue. That's the complication that we all have to get our heads around. And the same down here, it'll either be green, green. This is always going to be green because it's always going to be a down movement. There are no up movements, so that's going to be unique. These two paths at each end are going to be unique paths. Unique ways of going through the woods, unique ways of following the caribou across the tundra. Yeah, they used to follow the caribou across the tundra by taking a moose shoulder blade and putting it on the fire and letting it crack. Same kind of pattern. It seems random, which way you want to go. Start out here, where are we going to end up? Could be random. And the idea of randomness is indiscriminate. And the way of characterize indiscriminate is an information structure like this with plausibility, with probability. Okay. More words. But all down movements on this graph are going to be occurring at a rate of 75% of the time, according to this hypothesis number 2. This gets laborious after a while, and infinite patience might be required, yes, but take the time to write it down in the notes. It's very helpful to do that. All up movements are 0.25, 0.25. We're not putting any gaps in anything here. We're just going to do it all. There we go. As the time goes by and the paint starts to peel and the grass starts to grow. There we go. So now we have a complete story about all of the different ways the novel can end. I mean, simple as that. We don't know which way it will end. We know with probability. Okay. So here's where we go. Create another column over here and record for each one of these nodes. Whoops, don't want to lose all those guys. for all of these different nodes, the number of ups it takes to get there and the number of downs it takes to get to these endpoints. And we'll just put this up here as ups, and U for ups and D for downs. So going up, up, up. Okay, yeah, 3 times, 3 ups. How many downs? 0 downs. So we're just doing some bookkeeping here. And for the next one, it's 1 up, 2 up, 1 down. Well, that's one path. Just put a hash mark here. Oh, we can also get there a couple of other ways. We can go 1 up, 1 down, 1 up. Well, that's another hash mark. We could also go down, up, up. Another hash mark. 3 ways of getting there. I don't think there's any other ways of getting to this particular point. You can check that out yourself. But in every single one of those ways, it's always going to be 2 ups, 1 down. Always. Let's go down to the next one just to flip this. Okay. To get here, well, we could go 1 up. We can go up to here, down to here, down to here. Well, that's one way of getting there. Hash marks again. We could go down and up and down again. It's another way of getting there. I hope you see some symmetry going on here. We can go down, down, and up again. Oop. Another way of getting there. In each of those ways, it's 2 downs, 1 up. 1 up, 2 downs, down, up, down. It's going to be 1 up and 2 downs. This is what Jabob Bernoulli saw. He saw this kind of a pattern going like, oh goodness, I know how to count again. I said it's about counting, and that's all it is. And at last but not least, there's only one way of getting 3 consecutive down movements or 3 consecutive observations of land. That's the other way we can look at this. And that means 0 up and 3 down. So we're almost where we want to be. I now want to ask, so this is literally the number of paths. 1, 3, 3, 1. That up here so we can create a little more real estate on the side. Now, what is the probability of one of those 3 paths, one of that one path? Well, let's look at the 3-pather. That is 1 up, I'm sorry, that's 2 up, that's 2 25s, 175, 2 25s, 175. Is this suspiciously like what we did before? Well, okay. Our data that we actually sampled, let's look at that for refresher, was this. Almost looks like a smiley face inside of a smiley face. It's 2 up and 1 down, where up is water, down is land. Okay. Notice we're doing consecutive abstractions here. Yeah, colors and ups and downs and letters and so on, but it all boils down to 2 up and 1 down. Remember that? And we figured out how many ways can we get a blue and raised it to the 2nd power. How many ways can we get a land, a green, raised it to the 1st power? So these will end up being powers. But instead of the actual ways, we're looking at them as the proportion of times, the proportion of all ways of getting any of these. And actually, there are always 4 options in our hypotheses. And we're sampling 3. So 4 to the 3rd. There's 64 total possible ways. That's neither here nor there, and you don't need to have that. That's just a little aside I could use later on to check some math. Draw a line here. The probability of one path is going to be by the counting rule that we used to use for each probability proportion of times, of total times, is 25%. And for each 25%, it's 2 of those 25% raised to the 2nd power. 25 of 25, 75 of 25 of 25 will get us a probability of a single path. So we can code that in. Well, we can use this actually. P raised to the 2nd and minus P to the 1st. Okay, just we're gonna do that. P to the number of ups that we observe. We're actually observing 2 in this case. That's why I picked this one. And we're only observing 1 down, 1 green in this case. 2 observed, 1 observed. And instead of the number of raw counts, we're using P instead, okay? 25% of 4, 75% of 4. Remember that? Okay, it's going to be the same idea. So we're still learning how to count here a little bit. So the probability of one path is going to be 25 squared, the magic of exponents, 25 times 25, because we have 2 blues. And 75, 1 minus 25, you have 1 water. That's just one path. The problem is, how many paths do we have with this probability? And that's another counting principle. Here it's like these are all both up and up and up. Oh no, up and down. And that'll give us a number. And we should be able to calculate that number. I think I calculated it as 4.6875. You can check that. Check that out. Take a couple of seconds here. Take a short break. Well, that was a fast break. And there it is. But check it. Okay. Now the next one down is going to be a little bit different. It's going to be just following this approach. Similar things will be done similarly. So instead of the 2 and the 1, it's going to be 0.25 raised to the 1st, 0.75 raised to the 2nd. Guaranteed it's not 4.6875. Okay. Okay, now we can get rid of the tree. We can just do the math over here. So that the probability of seeing 2, in our case, I'm going to get rid of this first, of data given an hypothesis. And in this case, we're looking at the probability of seeing 2 up or water, 1 down or land, given hypothesis of 0.25 is going to be this lovely number right here times this number. There's 3 of them. There's 3 paths, 3 separate paths, each with their 4.68%, 7, each with their probability. So this probability has to be equal to, there's 3 of them, just multiply 3 times 0.0467875, and we should get 0.14, approximately 14%. The probability of data given hypothesis. Now, your homework in your notebook would be figure out the rest. And I'll give you a couple of minutes to do that. Well, you could be computing these all day and get different data combinations. But actually, none of these matter. None of these matter. That should be your answer. And the reason is, what did we collect? We only collected 2 water, 1 land. The correct answer should be something that says, okay, for these paths, for these 3 paths, this particular data, instead of going down through all the nodes of this tree, figure out these nodes now for different values of P, for values of 0.50 and 0.75. The 0, 1, 1 hypotheses don't matter because we're going to always come up with 0 there. Okay, the probability either will be up 0 or down 0. And when anything's multiplied by 0, it's always going to be 0. So, okay, fine. So we're only going to be interested in these 3 paths. These 3 paths and these 3 paths only. And if we just write them out, we're going to be looking at this path, this path, this path, or this path, this path, or that path, or this path, or this path. Those are going to be the 3 paths. So it's either going to be up, down, up, down, up. Just using different colors here. Down, up, up. What do all these paths have in common? 2 up, 1 down. Why are we only using 2 up, 1 down? Because our data is 2 water, 1 land. That's why. Thus, only these paths matter. But now we have to fan these paths across all 5 hypotheses. And when we do that, we have this kind of a grid. We have P 0.0, 0.25, we just did, 0.50, 0.75, 1.00. Now we can immediately figure something out, but let's put in the probability of an hypothesis. And this time, let's make it proper. Let's say that can happen 20 for, that can happen 20, that can happen 20. Each of them can happen in a uniform manner at 20%, because now we're playing with probabilities instead of raw counts. Add that up, it's a proper prior. This has been our experience. We'll go with it. Our experience can change as we update data. That's the process of learning. And what are we learning? We're learning about how the data is structured across all of these different ways of thinking about the data. 0, 25, 50, 75, and 1. All of those different ways. And now we have a very complete picture given all of our assumptions. And now we can do something else. We can do the probability of the data given a hypothesis. Remember what the data is. This is the same as saying the probability of 2 water or 2 ups, 1 land or 1 down, given any old P we want, any old hypothesis we want. And we already figured out this number. It was 0.141 for that. We can calculate the others just as easily by substituting into this same formula, different values of P. Well, the first one value of P will be 0 raised to the second power times 1 raised to the first. Well, that's going to be 0. That's going to be easy. We'll just go straight over here. 0 down. And it's going to be the same down here. Why? Why? Because the number of ups will be 0 instead of the number of downs. So that makes our computational life fairly easy here. And we can fill in these two by calculating over here using the same formula with different values of P. So the next one, it'll look more like this one. It'll be 0.50 raised to the second power. Remember, the 2 stands for the 2 waters, the 2 ups. 1 minus is 0.50 raised to the first power, 1 down. There will be 3 of these. And if we do the math, 50, it's actually 50 cubed. There's 3. Got this. Now check this out on your calculators at least. I get 0.375. And then we also have to do 0.753 times 0.75 squared, 1 minus 0.75 to the first power. Again, we do this on our calculators. Remember, 1 minus 0.75 is, if we go 75% of the time up, the rest of the time we go down, 25% of the time. That's 1 minus 0.75. And I think we get 42 answers. I think we get that. Check your math. My math categorically is always weird and wrong. Do it on a computer. Hopefully I do that right. So I'm going to deposit those right here. I'm just going to round this up. Okay. Now the next thing is the thing that we also use our counting principle for, we're going to use again here. We're going to multiply these two together. And this is going to be an important number for us. We're going to say that both this hypothesis of 0 and this probability of seeing the data given that hypothesis is 0, both and both and, or one each, and the other we multiply those. Just like we did with the P's, just like we did with our counting 2 lectures ago. So we have the probability of data given hypothesis times the probability that that hypothesis even happens, which is 0 times. We get 0 times 0 is 0. And what do we get here? What do we get here? We get 0.2 times 20% of the time that hypothesis will be seen. And when it is seen, the data given that hypothesis will happen 14.1% of the time. And if we multiply those together, we get in another instance, in another universe, 50% is our proportion of ups, 50% down. That's a different universe. And that also happens 20% of the time. And we will see this kind of observation given this 50, 37.5. When we see them both together, which is the correct way of looking at this, this is 7% of the time in that universe. Other things could happen, but if that bag contains 50% blue, 50% land, if the globe that we have roaming around and we cut out the proportion of water and land on the beach ball, they're exactly the same amount, then that's that would be the probability. And 0.75 happens 20% of the time, and the data in the presence of that particular hypothesis happens 42.2% of the time. And lo and behold, I don't think anybody's surprised by this. And 0. Now, just like what we did before. Where we took the ways and added them up. And then we took the ways and divided them by how much they added up to in total. And we got our plausibility numbers that way. This way we were able to compare on an absolute apples to apples as opposed to apples to beef jerky, totally different, which is like purple to orange. Instead of that kind of comparison, we got apples to apples. And not Golden Delicious to Macintosh, Macintosh to Macintosh from the same tree on the same branch. All right, that's very close comparison. That's what we were looking for. Hardly ever happens in nature that we can get that, but we pretend a lot here. So if we add up 0.0844, 0.0750, I get 1594, and add to that 0.0280. Yeah, I'm using my calculator. Okay. I can't do this one in my head. I get 1876. So that's the data fanned across all of the hypotheses. And we'll have a name for this 1876 one day. But right now, let's compute the probability of seeing the hypothesis given the data. This ends up being Bayes' theorem, but it's the probability ends up being the relative size of each of these numbers of the 02, the 07, the 08 against one another. So we're going to take the 0.0282 and divide it by 0.1876. And we get what? Oh my gosh. 0.15. Oh, that's 0. That is 0.0282 divided by 0.1876. 15. Take 0.0750 and divide it by 1876 decimal places, of course. You come up with almost exactly. There's some rounding here, but it's exactly the 2 decimal places. This number, 40%. Take 0.0844 and divide it by 0.1876. Yes, 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 you know what the answer is. 45, just like last time. So, because logic is logic is logic, the two ways of conceiving this problem end up with the same result. That's deduction. That must mean they are representing the reality in almost the same way, but they're represented it correctly, just slightly different variations on a theme. They're not a difference in kind, they're a difference in degree of complexity. This model is completely equivalent, we would therefore say, to the model we built in, yes, lecture 1. Well, that had to be a lot of fun for you. It was great fun for me. Some key takeaways here, and we can do inference on this, of course. We're going to play with the inference in part 2 of this lecture. We've done enough right now. done enough damage to our brain cells for sure. But we just took the example from the first lecture, and now we have a new way of doing this. And there's actually a formula for this. And it's called the binomial distribution formula. Write it out here, the probability. We've been doing this all along. The probability of seeing x ups n minus x downs, the up, the down, the water, the land, given a proportion of x's. And this actually is the answer to our question. Amazing. The probability of this, which is what these numbers are in this column, we can say it was 3. Well, there's actually a formula to get that 3. N is 3. 3 tosses of the globe. 3 draws of Lucky Charms from the bag, replacing those charms back in the bag, which is the real reason why we get this lovely replicating, beautiful closed form structure. Ups and downs and ups are equivalent to downs, ups, ups. They get to the same place because it's done with replacement. And you may know this story. Story of a combination. This is what we're going to program into the computer. Let's do one of these. Probability of 2 and 3 tosses minus the 2 waters, given P equals 0.75 equals 3 factorial, which is 3 times 2 times 1. Notice how blithely or blithely I am assuming you know what that means. And you should just haul it out of memory, or you could look up factorial. Oh, that's an R, isn't it? In any citation on the internet. Okay. And X is the number of waters, 2 factorial. 3 minus 2 factorial. There are 3 people who can enter the classroom. How many ways can they enter the classroom? Well, 3. Okay. Then 2, and then 1. All right. 3 times 2 times 1 is 6. But that is cut into portions because sometimes they can come in 2 at a time. 2 factorial. So we got to take the 6 and divide it by at least by the 2. But there's 2 and then there's 1 left over. That's that 1. But that's just 2 times 1 is 2. So 6. But if they come in pairs, how many ways can they come in? 3 ways. Try it with your team. All right. Teams of 3 can definitely do this. How many different ways can a team of 3 enter coming in pairs? Okay, that's all this is saying. P is 0.75 raised to the second power, 1 minus P to the 3 minus 2 power, or 1. It's the same as 3 times, what's 0.75 squared? I asked the crowd, and the crowd will verify that it's 0.5625. And this will be multiplied by 0.25, because that's 1 minus 0.75 is 0.25 raised to the 1 power. So we get 3 times 0.5625 times 0.25. I get, 14.1. Isn't that interesting? Just like the first case. They're very symmetrical, that's why. Right there. And 3 times this number equals 1 times 3.423. 4.2. I've been rounding. Yeah, close enough. I make that 3. Won't change things very much over here. Change just a little bit. You multiply that times 0.2. How probable is it to see that hypothesis? And you get the probability of both of those, the data given the hypothesis and the hypothesis existing at all, 20%. You get 0.0844. Okay. Add those up to 1876. Don't forget this step. And you get our original numbers. What have we done? What have we done to ourselves? We've learned a little bit more about counting here, the number of paths. We motivated this with data going up 1, 2, 3 different paths using our globe tossing thing, all inside of a thought structure, a mind. This doesn't exist in reality. This is the way our mind processes what might happen with these observations. And then it abstracts from that, these particular observations to come up with a number of paths that we use to calculate this number, and this number. Boy, no wonder we're always confused all the time. There's so much going on here. But I hope this unpacking of it helped a little bit. The number of ups, the number of downs, the number of paths, the probability of each path. And here we only needed to look at this one because of this one refers to the 2 water, 1 down observations that we have. That's what we actually observe. If we added another observation, we have to go up and down again, up and down again, up and down again, up and down again. Don't want to do that. This is good enough to understand. Boiled all of this down to a formula where even the number 3 has a formula in terms of what is called a combination. Remember, 3 members of a team coming through the door in pairs. How many ways can that happen? Just do it. And then say, well, you got 4 people coming in the door in pairs. How many is that? You can, instead of a 3, it's a 4. See if those things play out. They have for about 300 years, so they should still continue to play out. I'm going to leave you with that, and we'll pick up the reins on this in part 2, where we'll take this table put it into Excel, and do a couple of visualizations of it. And the couple of visualizations will actually layer one on top of the other. And learn a little bit of Excel, how to play with it, what you already know about Excel, name ranges, of course, but the structure, the thinking, the engineering of how to implement this on a computing platform like Excel. That's what we're going to do next. And I, again, thank you very much for your kind attention and listening to this long drawn out affair. I hope it's helpful. Be sure you do the reading in the chapter. There we go. This chapter. The binomial ups and downs, chapter 4 of the book that accompanies this, which is wgfoot.github.io. Let me put that on here for those of you who might not have seen this in the description. You know, the URL can be upper or lowercase, doesn't matter. It just sees it all as one thing. I think that should get you there. And yes, it will. Make sure you do it with dashes, not underscores. And that will get you to the book, and you'll have a navigational panel on the left to help you. Again, back to our heuristic structure. This is always where we're starting and where we're going back to. It takes into account our 5-step analytical process. Take care, and again, thank you for your kind attention.